Welcome back to another deep dive. Today, we're tripping away pretty much everything we understand about modern industry to look at something that, quite frankly, just shouldn't exist.
You really shouldn't.
If you think about the history of engineering, the way we progress, this feels like a glitch in the timeline. We're going to try and transport you to the beaches of Tanah Baru. It's in the Bulukumba Regency of South Sulawesi, Indonesia.
And it's a place that, the sources describe it as just an assault on the senses, but in the best possible way. The air is heavy, and not just with, humidity.
Right.
It's got this very specific industrial perfume. You've got the salt spray coming off the floor of sea, and that's mixing with this sweet, kind of acrid smoke from burning resin.
And the sawdust. That smell of fresh-cut wood.
Exactly. But it's this sharp, almost tannic smell of ironwood sawdust specifically. It's everywhere.
And the soundscape.
Yeah.
That's what really got me. You think of a modern shipyard, maybe in Korea or Rotterdam, and the background noise it's a hum. It's electric welders, the beep of forklifts, maybe the whine of a CNC machine.
Yeah, it's mechanical, it's precise.
In Tanah Baru, it's percussive.
Mm-hmm.
It's this constant, rhythmic thud, thud, thud. And that sound is the adze.
Which is, let's be honest, it's basically a prehistoric tool. It's a blade, but it's set perpendicular to the handle like a hoe.
But yet, with this ancient tool rising right out of the white sand, and I want to stress this, there's no dry dock, no concrete slipway. There are these massive wooden skeletons.
They're just huge. We are talking about vessels that are 40 meters long, weighing up to 350 tons.
Just to give you some scale on that, that's significantly bigger than the Mayflower. These are colossal ocean-going ships.
Absolutely.
And here is the hook. This is the thing I have been trying and failing to wrap my head around since I started reading the research for this. These ships are built without a single blueprint.
Either. Not one. No blueprints, no CAD drawings, no schematics printed out on a plotter, no finite element analysis software running on a supercomputer.
That is, in any modern engineering context, that is terrifying. If you came to me and said you wanted to build a 350-ton skyscraper or a bridge with no drawings, you'd be arrested for criminal negligence.
You absolutely would be.
But here, the entire incredibly complex, hydrodynamically sophisticated 3D model of this machine, it exists solely in the mind of one person.
The Panrita Lopi, the master builder.
And that's the paradox we're really digging into today. We're calling this one the impossible ships.
Yeah.
Because logically, the cognitive load, the sheer mental effort of holding a design that complex in your working memory, it just seems impossible.
It does.
So we want to understand how this intuitive engineering actually works. Is it just a guess? Or is it some form of high-fidelity data compression that's been passed down for generations?
Oh, it's definitely the latter. And I think we need to dismantle this idea right away that this is primitive. It's not. What we're looking at here is a divergence in the evolution of engineering.
A different path.
A completely different path. Western engineering went down the road of explicit knowledge. You write everything down, you create standards, you make it so that, theoretically, anyone with the manual can do it.
Right, it's democratized.
The Conjo boat builders of Sulawesi, they went the other way. They went the route of tacit knowledge. It's embodied skill, it's passed down through oral tradition, and, just as importantly, through muscle memory.
Okay, so let's break this down. We need to look at the construction method itself, which is mind-blowing because it's completely backwards.
It is.
And we'll get into the magic, all the rituals, and try to analyze them as, project management tools.
Which they are. They function as quality control checkpoints.
And finally, we have to look at the specific design of the Phinisi rig, which is its own story of genius.
And that's a great place to start with a quick definition. We keep saying Phinisi, and, colloquially, everyone uses that word for the whole boat. But technically, historically, Phinisi only refers to the rigging. It's that very specific configuration of 7 sails and 2 masts. The boat itself, the hull, that has a different name.
Yeah, the sources get into the Polari hull and the newer Lambo hull, which we'll definitely get to. But, okay, for the sake of conversation, we'll use Phinisi for the whole vessel, but with the understanding.
With an asterisk. We know better.
We know better. Okay. So let's walk onto that beach in Tanah Baru. You're standing there looking up at one of these wooden leviathans taking shape, and you meet the Panrita Lopi. In the West, a naval architect is someone in an office, probably has a master's degree in fluid dynamics, Who is the Panrita Lopi?
The term the ethnographers who studied them use is a living library. And that's not poetic, it's literal. This isn't a job you apply for. You don't go to university for it. It is a strictly oral tradition, primarily among the Konjo people of these three villages, Ara, Tanabaru, and Bira.
So how is the knowledge transmitted if it's not in books?
It's osmosis. It completely bypasses the academic model. You don't learn by reading, you learn by doing and by watching.
The apprenticeship starts when they're kids,
Yeah.
right? Like really young.
Very young. You start at the absolute bottom. Your first job is sweeping sawdust for years. Then you might get to hold the tools for the master. Then maybe you're allowed to sharpen the adze. You are just observing. You watch the master for decades before you're ever allowed to make a critical decision.
And during that time, you're learning to hear the wood. That's a phrase that came up a lot. It sounds a bit mystical. But let's ground that. What does that actually mean in an engineering sense?
It means you're learning to understand material properties through direct sensory feedback, not by looking at a data sheet.
Okay.
So a modern engineer, they'll check the Young's modulus of a steel beam on a chart to know how it will bend. The Panrita Lopi. He strikes a piece of timber with a mallet.
And he listens.
He listens to the pitch of the sound it makes. That pitch tells him the density of the wood. It tells him the water content. It tells him if there are any internal voids or rot that you can't see from the outside. He is literally performing non-destructive testing with his ears.
That's incredible. And the measurements. They're biological. They're part of him.
This is what some call embodied architecture. He's not using a tape measure. He uses his body. The dipa, which is the span of his outstretched arms. The span from his thumb to his pinky.
How does that work for standardization?
It's crucial because it means the scale of the ship is always relative to the builder himself. He doesn't need a tape measure because he is the tape measure. The ship is an extension of his own proportions.
That's fine if you're building a bookshelf in your garage. But we are talking about a compound curve hull. This is the part I just cannot get past with the no blueprint thing.
It's a huge mental leap.
A ship's hull is an incredibly complex 3D geometry. It curves from the bow to the stern, obviously.
Yeah.
But it also curves from the keel up to the gunnel. And the rate of that curvature changes at every single point along its length.
It's a differential calculus problem in 3 dimensions.
Exactly. And if you get that curve wrong, even by a tiny bit, the boat lists to one side. It creates drag. The hydrodynamics completely fail. So how does he visualize that? How does he execute it without a guide?
This brings us to the most distinct, the most bonkers feature of their engineering process, the hull first construction method.
Okay.
And to really understand why this is so difficult, you have to compare it to how we in the West and, the Vikings and modern shipyards, how we've always built ships.
We use the skeleton first method.
Right. Standard shipbuilding 101. You lay the keel, the backbone, then you erect the frames, the ribs.
So you build the skeleton of the boat.
You build the skeleton. The ribs define the exact shape of the boat. It looks like the skeleton of a whale sitting there. Once those ribs are up and braced, the hard part is done. You just have to attach the planks to them. The planks are just the skin. The shape has already been determined by that internal frame. It's a very safe, very logical way to build.
Of course. Because if a rib is in the wrong place or has the wrong curve, you can see it immediately. Before you've even put the skin on, you can take it out and fix it.
Precisely. The Konjo builders, they do the exact opposite.
Which seems insane.
It is. They lay the keel, and then they start building the skin, the planks. First, they build the shell of the boat, just holding it up in the air with props, plank by plank. The ribs, the internal skeleton, are inserted after the hull is already fully formed.
Okay, stop. That seems incredibly risky. You're defining the entire 3-dimensional volume of the ship by building its surface area first.
That's exactly what's happening.
That means that every single time you pin a new plank to the one below it, you are making an irreversible decision about the final 3D shape of the hull.
Without any internal guide. You're just eyeballing it.
So the Panrita Lopi has to know, just from intuition, that at this point, 10 meters back from the bow and 2 meters up from the keel, this plank needs to curve inward by exactly 4 degrees. And if he's off by half a degree...
The 2 sides of the ship won't meet correctly at the stern. The whole thing will be asymmetrical.
It'll be lopsided. It'll handle terribly.
Imagine trying to build a barrel, but instead of setting up the metal hoops first and fitting the staves into them, you just start holding the wooden staves together in midair and hope they somehow form a perfect circle.
Right.
Now make that barrel 40 meters long and shape it like a fish.
It implies a level of spatial reasoning that is just
Mm.
It's off the charts. He's not just building, he's running a continuous real-time simulation in his head.
He is. And as he's doing it, he's calculating things like displacement and buoyancy in his head. He knows that as he adds planks, he's adding volume, and he can feel how that's going to sit in the water.
And he's doing all this with wood, which is an organic, non-uniform material. It's not like steel that has predictable properties. Every piece is different. It fights back.
It absolutely fights back.
So let's talk about that battle with the material. Because the tools they're using, they're not laser cutters or plasma torches. They are using the adze.
The adze really is the hero of this story. It's such a versatile tool, but it requires just immense skill to use properly. The builders in Tanah Baru, they can use an adze to shave off a millimeter of wood as smoothly as a modern electric planer.
And they're carving these massive, heavy planks to fit together so tightly that the sources say you can't even slide a piece of paper between them.
Not even a piece of paper. The joinery is that precise.
Which brings us to the fastening system. Because if you're building a shell first, with no ribs, how do the planks even stay together before the internal frame is put in? What's holding it all up?
This is where it gets really, really interesting. They use a technique called edge joining. They drill a series of holes into the edge of a plank, the thin side. Then they hammer in these incredibly hard wooden dowels, they're called pasak, and they leave them sticking out. Then they take the next plank and hammer it down onto these protruding dowels.
So the hull is basically a massive sandwich of wood and thousands of dowels. It's like it's stitched together from the inside.
It is. Thousands and thousands of these dowels. And traditionally, this is a really important distinction from Western shipbuilding, no iron nails were used at all.
Because of rust in the tropical saltwater.
It's not just simple oxidation, like you'd see on a rusty car. It's a much more aggressive galvanic reaction, especially with some of the acidic tropical woods they use. The iron corrodes, it expands, and it literally splits the wood from the inside out. They called it nail sickness.
So a wooden ship built with iron nails would slowly destroy itself.
It would. By using wooden dowels, and specifically dowels made of ironwood, which we'll get to, the fasteners have the exact same properties of thermal and moisture expansion as the hull itself. The whole ship breathes as one single organism.
The sources mentioned a specific detail about the waterproofing that I just loved. The bark gaskets.
The Baruch bark. This is pure genius. So between the planks, before they're hammered together, they insert these thin strips of a specific type of tree bark.
Okay.
Now, when the ship is launched, the wood of the hull naturally absorbs water and swells, which tightens the joints. But this bark, it swells even more than the wood does. It creates this incredible compression seal. It's a self-sealing system.
Wow.
It relies on the material itself knowing what to do when it gets wet. It's a kind of material memory.
Which is a perfect segue into the materials themselves. We absolutely cannot talk about these ships without talking about kayu ulen, ironwood.
Eusideroxylon zwageri. This wood is less of a plant and more of a geological force. I mean, it has a density of about 950 to 1,100 kilograms per cubic meter.
Which, for anyone listening, normal water is a 1,000. So This stuff, it sinks.
It sinks like a stone. It's almost impervious to termites. It's highly, highly resistant to saltwater rot. It's one of the most durable woods on the planet. But
There's Gatch.
Working with it is brutal. It has an incredibly high silica content, which means there are essentially microscopic particles of glass embedded in the wood grain.
So it just shreds the tools.
Instantly. The sources describe sparks, literal sparks, flying when modern steel saw blades hit it. So the builders, they spend a huge portion of their day just standing at a grindstone, sharpening their adzes.
And this wood is used for the most critical parts, right? The keel, the main structural members.
The backbone, because it provides the kind of rigidity you'd normally only get from steel.
But you can't build the whole ship out of ironwood. It would be way too heavy and, frankly, too stiff.
Yeah.
A ship needs to be able to flex a little in the waves, or it just snaps.
Exactly. It would be like building a skyscraper out of solid glass. So for the internal frame, for those ribs that they put in later, they use a different wood, usually bitty wood. And this is where the intuitive engineering moves out of the shipyard and into the forest itself.
Okay.
They don't just go cut down straight logs and mill them into boards. They go into the forest and they look for trees that are already curved.
They're literally shopping for shapes.
They're shopping for geometry. If they need a frame, a rib that needs to curve 90 degrees at the bilge, they will walk through the forest for days until they find a branch or a tree trunk that naturally curves at 90 degrees.
Which, from a structural engineering perspective, is far superior to just skim bending a straight plank.
infinitely superior. When you steam bend wood, you're putting immense stress on the fibers, you're weakening them. When you cut a curved shape out of a big, straight log, you're cutting across the grain, which creates all these weak points.
Right.
But if you use the natural crook of the tree, the grain of the wood flows continuously around that curve. It's nature's own carbon fiber layout.
You're optimizing the biological structure of the tree for the mechanical structure of the ship. You're not fighting the material, you're collaborating with it.
And this connects so perfectly to the spiritual beliefs that the sources highlight, the concept of jiwa, which means soul or life force.
They believe the wood retains the spirit of the forest.
They do. And, a modern engineer might just dismiss that as superstition, but step back and look at the behavior that belief dictates.
It dictates respect for the material. You don't just waste a piece of wood that has a soul.
Correct. And you don't harvest it recklessly, you handle it with a specific protocol. If you believe the tree is alive, you are much more likely to inspect it for defects, to ensure it's seasoned properly, to cut it in a way that honors its inherent strength. The myth functions as a quality assurance manual.
That is the perfect transition to what you call the magic is math part of this, because the entire construction process is just absolutely punctuated by rituals. It seems like every time they pick up a major tool or join two big pieces, there's a whole ceremony.
There is.
And I want to argue that these aren't just for good luck. They are hard-coded structural milestones.
I completely agree. Let's look at the very first one, the Anatara. This is the joining of the keel. This is maybe the most critical moment in the ship's entire conception.
And this is where they view the keel as male and female, right?
Yes. The forward section of the keel is considered male. The aft section is female. So their joining is seen as a marriage or a conception. But look at the engineering requirement here. The keel is the spine of the ship. If it isn't perfectly straight, if those two pieces aren't perfectly aligned, the entire ship is doomed before you've even laid a single plank.
It's the foundation. If the foundation is crooked, the house falls down.
Precisely. And a key part of this ritual involves drilling a hole called the posse.
The navel.
The navel. They drill this hole at the exact geometric center of the joined keel. Now, ritualistically, this is the umbilical cord that connects the ship to the creator. But think about what that requires the builder to do physically.
He has to find the precise center.
He has to locate the precise geometric center of the keel. That point is the ship's center of gravity. It's the reference point for all future measurements.
This is the most critical datum point on the entire structure.
It is. And by making this a holy moment, they place offerings of gold or fabric in the joint. They say prayers. You force the entire workforce to stop. You clear away all the noise and distraction. You focus everyone's attention entirely on getting this one coordinate perfect.
It's a mechanism to force mindfulness at the most critical step. If it were just another item on a checklist, you might rush it, but you don't rush a sacrament.
Exactly. The ritual ensures that this critical point is verified and double-checked with reverence.
Okay, so that's conception. Then you have the amosai, the birth ceremony, which is the launch.
Yes, the ship is treated as a living being with a full life cycle. The construction period is the gestation. The launch is the delivery.
And this involves animal sacrifice. The sources mention goats or cows, depending on the size of the ship, and the blood is smeared on the keel.
It is. It's very visceral. And again, you could look at that and just see superstition. But step back and look at the logistics of a launch. You have a 350-ton object sitting on the sand. You have no cranes, no hydraulic lifts, no shipyard railway. How on earth do you get it into the water?
You push it with a lot of people.
You and 300 of your neighbors. This requires what the sources call community engineering. The ceremony, the feast, the ritual slaughter of the animal, and the distribution of the meat, that is the payment mechanism. It's the social contract that mobilizes the entire village workforce.
So the ritual isn't just for the boat. It's for the people.
Absolutely. The Panrita Lopi isn't just an engineer. He has to be a community organizer. Without that ritual feast, that ship is staying on the beach forever.
And there are all these other taboos about timing, too. Things like you can only cut wood on the 5th and 7th day of the month, or don't work if a certain bird sings.
And those function like a modern ISO standard. They enforce a schedule and a set of rules.
Okay.
The timing for cutting wood often correlates with lunar cycles.
Which affects what? The tides.
The sap content in the trees.
Hmm?
You cut wood when the sap is low, it seasons better, it's less prone to rot and insect infestation. So by encoding this practical knowledge into a taboo, by saying it is bad luck to cut wood today, you ensure compliance across the board.
It's a much more powerful motivator. If you told a worker the sap levels are suboptimal today, he might ignore you.
Right. But if you tell him The forest spirits will sink the boat if you cut wood today. He listens. Every time. It's a fear-based compliance system, maybe, but it yields incredibly high-quality engineering results.
It's a robust system. I mean,
Yeah.
the proof is that it's worked for hundreds of years.
It absolutely has.
So, okay, we've built the hull using this incredible skin-first method. We've managed the project using rituals as checkpoints. Now we have to rig it. And this is where the name Phinisi actually finally applies.
It's the 7 sails.
7 sails, 2 masts. The folklore says the number 7 represents the 7 seas or the 7 layers of heaven. But the rig itself, what they call the standing gaff rig,
Yeah.
that is a piece of pure genius industrial design.
It really is. And to appreciate why, you have to look at the Western gaff rig that it evolved from. On a classic Western schooner, you have this really heavy wooden pole, the gaff, that runs along the top edge of the mainsail. And every time you want to raise the sail, you have to physically hoist that heavy pole, plus the sail, all the way up the mast.
Which is heavy work. It takes a lot of crew. And if that thing comes crashing down on a rolling deck, it can kill people.
Exactly. And in the Indonesian archipelago, you get these sudden violent squalls that come out of nowhere. You need to be able to reduce your sail area fast. Very fast.
So what was the Phinisi innovation?
It was so simple. It's brilliant. They fix the gaffs permanently in the air. They're just lashed to the mast. They don't move up and down at all.
We're just up there all the time. So how do you set this sail?
The sail just hangs from rings that slide along the gaff. You pull it out like a shower curtain on a rod.
That seems incredibly simple and effective.
It's absolutely brilliant. If a storm hits, you don't have to wrestle with lowering a heavy, swinging spar on a pitching deck. You just pull a line called a brail, and it bunches the sail up against the mast. You effectively close the curtain. It's a huge safety feature.
And the sources mentioned a secondary benefit that's just as clever.
Yeah.
Cargo handling.
This is critical. You have to remember, these ships were the backbone of inter-island trade. They're going to remote islands in Maluku, Nusa Tenggara, places that might just have a rickety wooden jetty, if that. No cranes on the dock.
Right.
Because the gaff is permanently fixed up there and it's structurally sound, it doubles as a crane boom. They just rig a block and tackle to the end of the gaff and use it to lift heavy cargo like logs or sacks of clothes right out of the hold and onto the dock.
It's a self-unloading truck. The ship carries its own infrastructure with it.
It is. The entire design is perfectly, elegantly adapted to the specific environment and economy it serves.
And the masts themselves, they aren't always just single poles like on a Western ship.
No, often they use a tripod or a bipod mast, so 2 or 3 poles that meet at the top in a triangle. This is another really clever bit of design.
Why do that?
Because it largely eliminates the need for what's called standing rigging, all those complex wire shrouds and stays that you see holding up a Western mast. A tripod is an inherently stable structure. It distributes the load directly to the sides of the hull. It's simpler, it's stronger, and it's much easier to maintain when you're in a place where you can't just order a new spool of stainless steel wire from a catalog.
So what we have here is this perfect marriage of a hull that can handle rough seas and a rig that is incredibly versatile, safe, and low maintenance. But nothing exists in a vacuum. History moves on, and the Phinisi has had to evolve.
Yes, the 1970s and 80s were the huge turning point. And that was the arrival of the cheap, reliable marine diesel engine.
You can't stop progress. But slapping an engine onto a traditional sailboat isn't as simple as it sounds, is it?
Not at all. And this brings us right back to the shape of the hull. The original Phinisi hull, the one called the Polari, was a true double-ender. It was very rounded at the stern, and it had these 2 rudders mounted on the sides on the quarters.
It was designed to slip through the water.
Exactly, and to roll with the waves. But a propeller needs a clean, straight flow of water to work efficiently. If you stick a propeller behind a big, curved stern...
You get a lot of turbulence. It's incredibly inefficient.
Right. So they had to change the hull. They adopted a different design, the Lambo hull. They basically chopped off the curved stern and made it a flat transom. They extended the keel straight back and hung a single large central rudder behind the propeller.
Which is much better for a motor vessel.
Much better. And this is what we see today. Most modern Phinisi are actually motor sailing vessels, or what they call KLM, Kapal Layer Motor. The sails are often still there, but they're mostly for stability or for saving a bit of fuel on a long passage. The engine does the real work.
But now there's a new evolution, and this one is driven by us, by Westerners, by tourists.
The live-aboard boom. Places like Raja Ampat, Komodo National Park, these are some of the most incredible diving destinations on Earth. And the market demands luxury. They want to sail on a traditional pirate ship, but they also want air conditioning, ensuite bathrooms with hot showers, and a sun deck with beanbags.
I've seen pictures of these boats online. They are stunning. They look like floating boutique hotels.
They're beautiful, but from an engineering standpoint, they represent what the sources call a stability crisis.
Let's get technical here for a second. Why is a tourist boat so different from a traditional cargo boat in terms of stability?
It all boils down to one thing: the center of gravity, or kg. A traditional Phinisi was designed to haul dense, heavy cargo. Things like ironwood logs, bags of cement, sacks of rice. Where does that weight sit?
Low, very low, down in the bottom of the hold.
Exactly. And that heavy weight low down acts like the ballast in a modern keel. It pulls the ship's center of gravity way down.
Which gives it a huge righting arm. If a wave rolls the ship, that low weight wants to pull it back upright.
A massive righting arm. The sources suggest a traditional cargo Phinisi had a stability range of around 110 degrees. You could practically tip it over on its side, and it would still recover.
But a tourist boat?
A tourist boat is the opposite. It's full of air, you have cabins, hallways, a big dining saloon. And worse, we put heavy things high up. We add an entire upper deck for sunbathing. We put the freshwater tanks on the roof to gravity feed the showers. We put a heavy dive compressor on the main deck.
You're raising the center of gravity with every single modification.
Significantly. The data cited in some of the naval architecture studies is really stark. They show that on some of these modified tourist Phinisi, the stability range can drop to 85 degrees or even less. The angle of vanishing stability is reduced by over 20%.
That sounds absolutely terrifying. Vanishing stability, the point of no return, right?
That is the point where if the boat heels over that far, it doesn't come back. It capsizes. And because the original hull shape was designed for low-density cargo and low centers of gravity, it doesn't have the inherent form stability to handle this new top-heavy configuration without very careful and professional ballast management.
And this creates a huge conflict with the regulators, right? You have the BKI, the Indonesian Classification Bureau. They're looking at these converted tourist boats and saying, hang on, by our numbers, this isn't safe.
And this is that clash of engineering philosophies we talked about at the start. The BKI operates on modern, explicit, paper-based naval architecture principles. They want to see the blueprints, they want to see the stability calculations, they want to see the GM, the metacentric height, all calculated on paper.
And the Panrita Lopi says,
he says, I don't have paper, I have my eyes, I have my intuition. But the problem is, an intuition that evolved over centuries for building cargo ships doesn't necessarily translate directly to building three-story flirting hotels. The builder feels the boat is safe because he built it strong, but he might not be intuitively accounting for the complex dynamics of a top-heavy superstructure in a beam sea.
So you have this messy situation where the traditional method is clashing head-on with modern physics and modern safety requirements.
And modern bureaucracy. The result is that a huge percentage, some sources say up to 60% of these vessels, are not fully classed by the BKI. They operate in this kind of regulatory gray area. They're allowed to sail domestically, but they don't have the international safety certificates that a Western insurance company or tour operator would normally require.
It's a really difficult transition. But despite all these challenges, the world has officially recognized how special this tradition is. UNESCO listed it as intangible cultural heritage back in 2017.
Which was a huge, huge win. But it's really important to look at what UNESCO actually recognized. They didn't just list the Phinisi boat as a thing, they listed the art of boat building. That's a crucial distinction. They recognized the entire social and economic system behind it.
The Pungawa and the Sawi system.
Yes. This is the economic engine that makes Tanaburu work. The Pungawa is the project lead, the financier. He's the entrepreneur who finds the client, provides the capital, and takes on all the financial risk. The Sawi are the artisans, the specialized laborers, the plank benders, the caulkers, the riggers.
And it's not just a simple boss-employee relationship, is it? It's deeper than that.
It's a patron-client relationship. It's deeply woven into the social fabric of the village. The Pungawa often supports the Sawi's family. He might loan them money for a wedding or help with medical bills. The shipyard isn't a factory with a time clock. It's a community hub. The entire village economy rises and falls with the fortunes of the shipyard.
And that very system is now under threat.
It is, from two sides. First, there's the brain drain. The sons and grandsons of the master builders, they're going to university in Makassar. They want to be accountants or civil servants. They don't want to spend 20 years sweeping sawdust to learn a trade that breaks your back and pays less than an office job. The chain of transmission is breaking.
And then there's the resource drain. We can't ignore the timber issue. Ironwood is an incredibly slow-growing tree. It can take centuries to mature. You can't just plant a new forest and have it ready in 10 years.
Exactly. The impossible ship is facing the very real possibility of becoming actually impossible to build, simply because the raw materials are gone and the people who hold the mental map are retiring without passing it on.
So as we start to wrap this up, I want to circle all the way back to the core question. Why does this matter? Why should someone listening to this in New York or London or Tokyo care about how a wooden boat is built on a beach in Sulawesi?
I think it matters profoundly because it challenges our entire definition of technology. We have this bias where we think technology means microchips and AI and software. But the Phinisi is proof that the human mind, when trained and focused over generations, is an incredibly high-performance computer. It can run complex physics simulations. It can store gigabytes of structural data in a non-digital format.
It's a powerful reminder that we are capable of these incredible, complex engineering feats without digital aids. That the most powerful tool we have is the one between our ears.
And I think it also serves as a bit of a warning. As we move faster and faster toward AI-driven and automated design, we are gaining incredible speed and efficiency. But we are losing what you could call tactile engineering. We're losing the ability to feel the material, to measure the world with our own hands.
When the Panrita Lopi is shaping a plank, he feels the tension in the wood fibers through his adze. He knows the limit of the material because he is physically intimately connected to it. A naval architect looking at stress concentrations highlighted in red on a computer screen. They don't feel it in the same way.
There is a soul in these ships. And it's not just because of the ritual. It's because they are literally handcrafted piece by piece by a community. They are imperfect, they are organic, and they are incredibly resilient.
I want to leave the listener with that final image from the sources. The launch, the Inosi ceremony.
It's such a powerful scene. Imagine the heat, the humidity, the smell of the sea, and the cooking food. You have 300 men all pulling on these thick ropes, chanting in unison, and this 300-ton mountain of wood, which was just a pile of logs in the forest a year ago, it suddenly lurches forward, slides down the beach on rollers, and hits the water with this huge splash. And then it floats. It sits perfectly on its lines. It works.
It's that moment. The moment where the impossible becomes real.
It is, and it's a moment of human ingenuity and community spirit that I think we should fight to understand and preserve.
If you want to see this for yourself, and I really think you should, just look up videos of a Phinisi launch or photos of the standing gaff rig. It really puts everything we've talked about into a stunning visual perspective.
Absolutely. It's one thing to talk about it, another to see it.
Thank you for joining us on this deep dive into the intuitive engineering of the Phinisi. We'll see you in the next one.